Hi everyone, I'm Yunhui. Today I'm going to present our work, a pragmatic approach to membership inferences on machine learning models. Recent progress on machine learning has enabled applications such as autonomous driving, face recognition, and natural language processing. However, with these applications, more and more sensitive data are used to train the models. The training data could be photos, demographic data, location data, or even medical records. This uncovers a range of new privacy risks associated with inferring sensitive machine learning training data. One example of these risks is membership inference attack. In a membership inference attack, an attacker queries a machine learning model in order to infer whether a specific target record was part of the training dataset. In this paper, we consider a black box setting, where the adversary has no access to model parameters, but can interact with the model by submitting queries and observing the prediction vectors, which is a vector of probabilities for each classes. One example of the black box setting is machine learning as a service platforms, such as Google Cloud. Such platforms allow users to train a machine learning model and make it available for others to query. In prior works, the goal of the attacker in the machine membership inference attack is to achieve high attack precision on all of the records. We call this an indiscriminate attack. In an indiscriminate attack, the goal of the attacker is to infer the membership of all the records in the training dataset, and the attack success probability is the number of correctly inferred records divided by total records in the dataset. This calculation reflects an average privacy risk of records in the target dataset. However, precision of indiscriminate attacks do not always give a complete picture of the privacy risk, especially when the attack precision is low. For example, suppose an indiscriminate attack achieves 51.7% precision on a population. What does this mean in terms of privacy risk? Actually, there could be two possible explanations. In the first case, all the records have a probability of 0.517 of having their membership status correctly inferred. This indicates a relatively low privacy risk because the attacker does not gain much advantage over random guessing. However, there is another possible explanation. That is, 1.7% of the records are at high privacy risk, while the remaining ones have no risk at all. Actually, this case is concerning for these 1.7% of users with high privacy risk. In this work, we propose a pragmatic membership inference attacks, where the adversary carefully selects attack targets to minimize false positives. Instead of trying to achieve high precision for all the records, the goal of the attacker is to find some records that can be attacked with high precision. We believe this type of attack better reflects the privacy risk of individual users, especially for outlier users that have a higher chance of being successfully inferred. The adversary model could be summarized as follows. First, the user Alice randomly selects a training dataset from a population. She then trains a machine learning model on the training dataset and makes it available for public query. On the other side, the adversary Bob selects a vulnerable records from the population and performs the attack only if he has high confidence in the record being in the training dataset. The probability of success for the adversary Bob is calculated over the randomness that he cannot control. In this case, it's the selection of other training samples and random initialization in the training process. We proposed a three-step attack for the adversary to perform the pragmatic attack. First, the adversary selects vulnerable records from a group of target records. These vulnerable records are usually outliers in the population, and the adversary could select them based on their features or train local shadow models to estimate how much influence each record has on the prediction of a model. In the second step, the adversary generates queries related to the vulnerable records and query the target models. This could be a direct attack where these queries are the target records themselves, because querying the records leak the most information about their membership information in the training dataset. Meanwhile, we also proposed indirect attacks, where the queries are similarly uncorrelated with the target records, and we demonstrated that some target records membership could be inferred even with similarly uncorrelated queries. Finally, the adversary only makes a positive membership inference if a target model's predictions strongly indicate the presence of the target record in its training dataset. Otherwise, the adversary makes no inferences. We performed experiments on 3 datasets, amnest, adult, and cancer. We tested the attack on both local models and Google Cloud Services, both in black box setting. Our experiment results demonstrated the importance of pre-selection of vulnerable records. These steps allows the attacker to achieve high attack precision even on well-generalized models. The pragmatic attack achieves 95.05% precision on the 27 selected records, while prior indiscriminate attacks imply barely above the baseline precision. The top right figure plots some of the vulnerable records in a well-generalized amnest model. Additionally, we performed indirect inferences by querying similarly uncorrelated enhancing records. The bottom right figure shows an example of an indirect inference. The membership of the first record on the left could be inferred by querying noise-like enhancing records on the right, which makes the attack harder to detect. We also demonstrated that regularization reduces the privacy risk but does not eliminate it. Increasing L2 regularization coefficient reduces the number of vulnerable records and attack coverage, but there remains one record that could be attacked with high precision. In conclusion, in this work, we considered a more pragmatic adversary who carefully selects targets and makes predictions conservatively. We proposed new membership inference attacks that allows a pragmatic adversary to identify vulnerable records and infer their membership with high precision. The pragmatic attacks achieved high precision on the selected targets, while indiscriminate attacks imply barely above the baseline precision. This work also shed light to new approaches of privacy protection. Since some records are more vulnerable than others in a membership inference attack, training data analysis and selection might be useful to complement existing privacy protection approaches and increase the protection on those vulnerable records. This ends our presentation. Thank you.